works. Hey, so I'm Ivan. I'm from Booking.com. I'm a dev there, and I'm here to talk about some of the scalability problem which we had at Booking.com and how we solved it. Right. So my talk is namely about the thing which we call Graphite processor internally. I'll explain what's that. It's actually, this is not the full name. The full is actually the event Graphite processor, right? And I want to start my talk with letting you know, so what's actually an event? Because an event for Booking.com is probably it is one of the most valuable source of data which you have, because lots of things is built on top of a stream of events. So what is an event? It's basically just a message with some technical and a business data. Right? So on the right-hand side of the screen, you can see an example. It's basically just a hash ref, like a gigantic hash ref with various keys. For example, in this case, what's the data center this message originated from? What's some information about what protocol was used? What's some wall-click messages, etc. To deliver those messages, we use a serial. This is in-house built serialization library, which I also I participated in. So in its development, it's pretty cool. Has some very nice benefits. So and the way we deliver messages is basically obviously we have many of them. I'll tell you what's the scale on the next slide. But we deliver them in a way that we group them together, right? So here, basically what I'm trying to say here is that we have we group them by second. So this basically array contains a number of messages which happen during a second, and we serialize this array. And why we do it this way? Because messages are big. They contain a lot of keys which are repeating. And by serializing them this way, we can basically more efficiently deduplicate data. So for example, there will be, for example, 1,000 messages with the key tuning, and we can store them only once and then only reference it. That's one of the features of serial. So, what actually events are used for? They generated at the source. So, for example, we generate event for each web request. For example, when you go to a search page at Booking.com or to a hotel page, this request will generate an event. We generate an event per cron run. For example, per send of a mail, per send of fax. We even have events which are sent by database servers. So various kinds. Right. And they all send to what I just named a transport. It doesn't really matter for the sake of this talk what the transport is, but its purpose is just to deliver the messages from its source to its destination. And we have multiple destinations, and most noticeably, one of the destinations is the monitoring system. So we use this flow of events to process them in a near real-time fashion. To extract relevant bits of information and to produce some graphs. For example, another destination is that we store those events for long-term storage and analysis. So, for example, our analysts use events to predict how much bookings we should expect at a certain moment of time. The A/B testing, Booking is very famous for doing A/B testing. The results of A/B testing is also produced based on the data which is contained in the event, and some other cases. So that's a very brief overview of what event is and what's used for. So coming back to event Graphite processor. So it's basically a distributed fault-tolerant system which aims to just generate Graphite metrics from events, right? So we have a flow of data. For example, we have a flow of data, and you want to see them not as the many messages, which is gigantic, and you cannot really see it, but you rather want to see it as a kind of single line on a screen, right? So and for that purpose, you can write a kind of plugin. We actually call it a monitor, and you can say that, hey, out of those gigantic messages, I want just fetch a single key, right? For example, this key will be a wall clock. I want to compute a percentile, so I don't know what you want to do. just like average all the things per second, and then send it to Graphite. Right? And that's the idea of Graphite processor. And the key is here is that this is a user-defined code, which means that the events, they are really kind of free format. There is no predefined structure, and people are free to put any kind of information there, right? So it means that if you want to have some kind of visibility on the system you're building, you just put some data into event, and then from the other side, you build a monitor which will fetch the data, right? So why I'm saying this is because what information we're actually producing is not always known for us as the maintainers of the system. And yeah, we have about like 260 monitors currently. And I already mentioned that we send events per second, right? So, and a Graphite processor also works on the per second base, right? This is also due to the nature of Graphite, where the slot which is available in Graphite is a second. And the scale of our system is so that we peak up to processing 500,000 such messages per second. This is a very big number, right? So it's really like gigabytes and tens of gigabytes per second. So that's it. And the kind of classical way since the very early stages, since the Graphite processor system exists, the way it works is basically here on the slide in these 4 lines of code. This is a pseudocode. So we get the by the way, like epoch is basically a second, right? So whenever you see epoch, I mean second. We get a second of events, then we go through all the monitors. We feed a second of events into the function, which is I call like run. And this run function, that's where the user-defined code is run. Then this code does some aggregations, produce the result, and then Graphite processor just send this results back to, sorry, not back to, but it's send the result to Graphite processor. So like very simple, very straightforward. And so at some point with this model, we start having troubles, and the troubles are due to our scale. So our data set become bigger and bigger because as the business grows and also as we have more and more systems which want to send events, the amount of events which we need to process is becoming more and more unbearable. So for example, at this time, if you take a second of event, right, and you try to deserialize it, deserialized size in Perl will be about 10 or 15 gigabytes, right? This is just 1 second of events. Right, and to crunch this amount of data, well, this is not easy, right? And since it actually takes quite a while to it takes more than a second to process 1 second of data, right? And this is why we actually to parallelize some processing to actually make the system be near real time. But so yeah, for that purpose, we group some monitors and we actually process them in a fork, right? So since we're talking about Perl, well, the multi-threading support isn't great, so we have to fork, right? But the problem with forking is that when you work with this amount of data, is that there is always a bit of first of all overhead, but also there is a copy and write logic, right? So for example, currently what we do is, what we used to do, we fetch in the base process, we deserialize in the base process, then we fork. And then the fork inherit the memory pages, right? And like it seems that there should be no double memory consumption, but like in practice there is always like a Perl place with the internal structure. For example, it increment counters. There is an auto verification. This all triggers copy and write logic, which copy pages. That means that we will have more and more memory overhead. And this goes to the point that basically machines runs out of RAM, right? Because, well, our top machine at Booking has about like 120 gigabytes. So with a scale of 10, 15 gigabytes per second, we can only process 10 seconds parallel. This is like if we have no overheads. In practice, we have quite a lot of overheads. In parallel, we can process maybe like 5 to 6 seconds, which is not good. So yeah, RAM is being saturated, and well, no RAM means nothing, and the box is kicked out of the cluster, means that we lose actual visibility, so no metrics are generated. So yeah, that's the problem. So we start thinking about, by the way, like guys, the team which maintained the system actually did various amount of tricks trying to make system work. For example, like one of the my famous one is they try to give advices to Linux kernel which group to kill first. So it is kind of less priority monitors. So like the most critical I kept alive. So like all these crazy things. But like it was all obvious that the design needs everything. And since basically the main problem which we have was that we have to deserialize a second of event, right? And we need to keep it in RAM to basically process it, right? And what if the idea was that what if we try to actually do it a little bit differently? Instead of deserializing the entire event, right, we try to process it one by one, right? So fundamentally, each monitor just has a bit of internal state. For example, a single variable if you calculate an average, right? And then each event when you process just add something to it, right? Like very, very simple. So and then instead of we thought like what we can try to do instead of moving this way, we process data in chunks. Let's try to just have we have some kind of iterator, right? And we can deserialize event, one event at a time, so there will be no massive amount of data in RAM. And in this case, the system would work like this. So we first fetch a second of event, then we somehow get the event, then we iterate over all the events, feed in event one by one to the monitor, right? This will be kind of a processing step, and then in the end, there needs to be a post-process. For example, you accumulated data for computing percentiles, and then you want to compute in percentiles, actually, right? And then you do a post-processing, and then here what you get the result, and then you send it to Graphite. Okay, cool. There is one problem is that we actually, in this way, we change an API, right? And taking into account that this is a user-defined code and we have 260 monitors, well, that's a problem. But like, okay, like let's bear with it for a second. And so yeah, that's the user API changes. So, apart of this change of API, which we'll have to address, there is also how we can deserialize events one by one. Right? We cannot start sending events. We cannot start sending events differently, because if we de-chunk our blob of data, kind of try to store data one by one, right? We will massively inflate the amount of space we store on disk, and also we transfer over the wire. This is like a really massive increase. So actually had a project which I briefly mentioned in 2015 in YAPCU, and it's called Serial Path. So it started as my spare time project, and now it actually grew to a full-scale production system. So what's the idea of Serial Path, and namely Serial Path Iterator? So it's a thing which lets you iterate over a serialized object. Right. So, for example, like if you imagine a nested array with hashes, right? You can say that, hey, currently I'm in the object number 0, right? And I have an option to actually either step in, meaning that I'll inspect the body of the object, or I have ability of step over. So by doing this kind of step over, step in, you can guide yourself to the right location. Then you can say, hey, from this location, just deserialize. Right? So yeah, you can iterate over an object, and then you can say deserialize. And this way you can you can really instruct only data which you need. And that's what we did. We basically saying that, hey, deserialize the full object. We first deserialize the first event, then we step over it, then we deserialize the second event, we step over, deserialize the third event, and so on. So yeah, if you're going to use it, from the very beginning, I want to assure that this is not S-streaming, meaning that you cannot, the Serial Path Iterator doesn't support streaming. You still need to have the full blob in place in order to be able to inspect. And yeah, there is some limitation. Please check it out. So, but we still need to rewrite our user code, right? And that's, once again, it's 260 monitors, right? And we decided to actually start with the system, which is much smaller in scale, but similar in design. It's a system, so at Booking.com we have so-called log. This is a system where you can see like all the years. For example, here you can say that like during the last 8 hours, that's the amount of years which we have. Since it's a commonly used feature, it's a commonly used tool. There is no user-defined functions. It's basically a single implementation. So we can start with it. That's what it is. So yeah, flow clone is an identical stack, same problem, but it's a smaller scale, meaning easy to migrate. That's what we did. So we migrated these bits of code, and we got a very promising result, right? So there was twice faster in processing and massive drops in the RAM, like 2 order of magnitudes. That's expected because we don't deserialize the entire thing; we deserialize it one by one. So. And then, okay, like we will have some problems with our event Graphite processor. Things are coming in, and we need a solution. Box running out of RAM. So let's move on. What we had to do, there was a plan. So first we had to freeze the development, the new coming monitors for some time while we're doing the migration. Then we will have to migrate all the monitors to the new API. Then we will need to run a full-scale test, roll out the system, and perfect. So how we approach the migration, right? So it was very clear that a single team wouldn't be able to deal with the migration. It will take quite a long time, taking into account that development is frozen, right? It was very clear that a team of like 2-3 persons cannot do this. That's why it was a decision. Okay, like let's do a hackathon. Like at Booking, we have a very nice culture with kind of collaborative culture. We can just call for people. Hey, like when you help, please help us, right? And there was 8 people who were involved in this hackathon, and they were able to migrate all these 260 monitors within just 1 day. Like there are some numbers, which was the delusion. That was a super good example of collaborative work. Inside Booking. So, and then we ran it in production. So we did the migration, we ran it in production, like nothing worked. It was really like a set, because like we used to have 80 seconds to percent 1 second, now we have like a 120, more than 2 minutes to percent 1 second. It's like, come on, like why this is happening? We started investigating, and we found like a very, very kind of, at the same time, very simple and a very funny thing. So here's the old system, here's the new system, right? So here we basically iterate over the array of events, and here we iterate one by one. Since this is all happens inside the fork, and the end of the fork, we do this POSIX exit. So the idea of POSIX exit instead of exit is that we don't call the destructors, meaning that the counters of the SVs, they will be not decremented, meaning that there will be no modifications of memory, meaning there will be no copy and write logic. So like if you here do a simple exit, like your Perl will start deallocating all the things. It will start decrementing counters, copying the entire memory set into the forked process just to immediately destroy it. This is kind of like it's a massive spike of memory usage and a massive spike of the CPU usage. So this is why we did the POSIX exit. But here's the thing, there is an implicit undef. There is implicit undef here. And this undef is actually called 500, like 500,000 times, and you need to deallocate 15 gigabytes RAM. So actually our system, like the code which is here was like very fast and very, very nice, but like because of this, like right, we had to actually deallocate things, and this is what killed our performance. And this was like a really, really, really sad moment of time, because well, like we can't do much about it, right? So like we allocated an event, we need to deallocate it. We need to spend time deallocating things. Like, what can we do? Is like, it was really, really sad. And like after a couple of days, we come back to this thing, and let's try to think once again. One of the approaches which we decided to take, let's try to get new hardware, right? At Booking, we currently have a hardware with 56 logical cores. And this CPU gives you about some very nice performance. And why I'm telling you this is because close. Somebody got lucky. So now since we don't have we basically have no RAM problem anymore. We now can actually fork more massively. We cannot fork before, because each fork implies an overhead, right? And this overhead means that we're running out of RAM. Now there is no overhead. The amount of RAM which we need is very small. It's like 100 megabytes per worker, right? So we can fork as many times as we want. And take into account that we have a new more amount of cores, we can fork more. This is what we actually did. We actually decided, okay, like let's fork more aggressively, and we actually fork 3 times more, right? So and that's what actually recovered our situation, because with the more forking, with still the same overhead, but since we forked more, it's more parallelization. We actually got two times faster system, and this is what kind of made us really happy. So in the end, like what did we get? The processing time, as I already told you, like dropped by 2. It's from 80 seconds around to process 1 second. Now we're about 40 seconds to process 1 second. The amount of RAM which we need to process 1 second is just like, well, it's almost negligible, right? Well, with this size, like I wouldn't care, right? And we were able to reduce the amount of machines we need, right? Both because of now we process faster, and also because the machines are more powerful, right? So from the cluster of 80 machines, we go down to a cluster of 30 machines. So that's the end of the story. The last slide. So what's the lesson learned? I put it in the engineering is a king and the collaboration is the queen. So this experience for me was the very good example of collaborative work, because there was really like 3 components involved. Like I got the idea, and then the team got actual implementation. Then there was a guys who actually helped the migration. Like if without any of these components, the work would be actually impossible. Especially with the guys who actually help us migrating things. So yeah, and the second learning is that like if individual things actually falls apart, like if you just try to think a little bit harder, they actually might work all together, right? And the last thing is, yeah, basically like a challenge everything, like a challenge the way it works, challenge the hardware use, yeah, like challenge everything. That's all what I had, and thank you very much.